again, we're going to work out a few mathematical relationships and a few problems for this particular module. Example 9.1, the cyclic rule. If we write the first law, du equals to dq reversible minus pdv, and now we make a substitution for the definition of entropy. ds equals to dq reversible over t. So then we substitute q reversible or dq reversible from this expression into the above, rearrange. We will see that dq reversible equals to TDS, and therefore du equals to TDS minus PdV. So this is a combination of the first law and the second law of thermodynamics. And hence, this is a very, very powerful equation. It can be used to derive a huge number of expressions in thermodynamics. Because of this ability to combine two powerful laws into a single one gives us a great latitude in utilizing it. One of the applications of this is to apply the cyclic rule to this equation. So we can derive another independent expression that is of very high praise and use in thermodynamics. So we apply the cross derivative rule in equation 9.14, and so you can look it up in the book at the corresponding pages, and then we can write the equation 9.15. That is, since du, a small change in the internal energy, is equal to the product of temperature and the change in the entropy minus the product of pressure and change in the volume, we can, because these are precisely defined equations, we can write the cross derivative as following: dou T by dou Vs. So you take the temperature, that is the second term, and the volume from the last term, so dou T by dou V, at constant entropy conditions, that is from the second term, is equal to minus dou P by dou SV. So the terminal letters are used in the first derivative, and the internal letters are used in the second term of the first derivative. So what does this mean? We can use this sort of relationships with du, dh, ds, da, dg. We can write a whole bunch of these relationships, and from each of them we can derive a cross rule product, generating a new expression of the change in the temperature with respect to volume at constant temperature in terms of pressure and entropy changes at constant volume. So this way we can generate a whole bunch of new equations. And this equation 9.15 that we just wrote is one of the Maxwell equations, and is widely used in a different sets of applications in thermodynamics. So how do we get this again? So look up in pages 174 to 175, apply the cross rule, and you should be able to get this. And so this is a very simple way to remember. The ends are used in writing the one derivative. The inner terms are used to write the second derivative. And remember to keep the sign intact. So here, the second term has a positive sign. The third term has a negative sign. And so the equation 9.5 shows that change in the sign. What does that mean? It means one variable and the other variable are related such that when the first derivative, the first term is decreasing, the second term is increasing, and so on and so forth. So next, example 9.2. 1 mole of argon is heated, constant volume, from 300 to 500 Kelvin. So 1 mole argon, we will assume is an ideal gas. Initial temperature 300, final temperature is 500 Kelvin. We are asked to calculate delta S for this transformation. So we think about the process at constant volume conditions. So somehow CV needs to be involved. So CV bar, we recall, is 3/2 R. We discussed this several times so far. Then we write the equation for delta S in terms of temperature. So delta S is integral Q reversible over T dt, and Q reversible in this process is a constant volume process is CV. Therefore, it's integral CV over T dt. And so the limits are T1 to T2. Those are the temperature limits. So notice the temperature in the denominator of the integral. So this needs to be carefully handled. So delta S then equals to, putting the limits T1 and T2, CV is 3/2 R because we start with 1 mole of argon. So N equals to 1, so 3/2 R over T dt. 3/2 R, of course, is constant, so they can be taken out of the integral. Then we integrate 1 over T dt, apply the limits. So we get 3/2 R ln 500 by 300. And so Kelvin and Kelvin cancel away. And therefore we get 0.766 R. Now we can substitute the value of R and get the units correctly. One thing to be kept in mind is whenever you take a log of a number, it should have no dimensions. That's the cardinal rule in mathematics. We cannot take a log if the number has any unit in it. So we have to use units of temperature, Kelvin on the numerator and Kelvin in the denominator. You can use any type of conversion factors we can use, but we want to make sure that the ratio is dimensionless in the end. So substituting the value of R, you get the corresponding 6.37 joules per Kelvin per mole. So looking at it, you would say, yeah, this makes sense because we have 1 mole of substance, so per mole. We assume ideal gas behavior, unless it's stated otherwise. And the units for the entropy is joules per Kelvin. And so everything works out quite nicely. This is a molar per mole change, therefore you have per mole units in there. So if 2 moles were used instead of 1 mole, then the CV bar equals to 3/2 R will become twice as much. So CV will be 2 times 3/2 R. So delta S will become twice as much. In other words, if we used 2 moles of an argon gas in this experiment, the delta S will be doubled as well. And so this is something important to keep in mind. This is how the mass, number of moles, is related to change in the entropy of the gas. Next, we take an example 9.3, where we're going to look at the entropy change at constant pressure conditions. 1 mole of solid gold is raised from 25 degrees centigrade, means heated, to 100 degrees centigrade under constant pressure conditions. So since we say constant pressure conditions, we should immediately think of CP, heat capacity change, heat capacity under constant pressure conditions. Calculate the delta S for this transformation. So CP bar is given as a function of temperature in this case. We are not assuming CP is independent of temperature. We are explicitly told CP is actually a temperature dependent function. So in this case, we write same as before, delta S equals to integral dq reversible over T dt. dq reversible in this particular case is CP because we have a constant pressure process going on. And since the CP is a function of temperature, before we integrate this expression, we write that explicitly. And so that is Cp over T dt will become 23.7 plus 0.0019 T over T dt. So this is explicitly written in terms of temperature, function of temperature. Now we integrate, you have two terms we get. The first term is independent of temperature. The first term has no temperature in the numerator, so it is 1 over T dt integration. The second term has a temperature in the numerator, cancels with that of the denominator, so we have integral dt. So this is something to be very careful about. So this is one of the points where we often see an error made. The temperature is not cancelled properly, and so get wrong answers in the end. So once you have integrated the expression, now we simply substitute the quantities, corresponding quantities, and we get the desired end results. And so that's, again, the units are joules per Kelvin per mole. So again, as we said before, we check if the units make sense. And so joules per Kelvin per mole, we start with 1 mole of solid gold. So the delta S is per mole. So that is correct. The units for the entropy is joules per Kelvin. That is correct. And moreover, we can also say that if we heat a sample from a low temperature to a high temperature, the entropy of the sample should increase. And in fact, delta S we got is a positive quantity. So this is consistent with our expectation. So this is how, when we get an answer, we should double check and make sure that it makes sense. At least the sign and the units of what we calculated should make perfect sense to us. Then we can assume this is reasonable, and double check your calculations, double check your units, make sure the integrations are done correctly, and we have not forgotten a variable here and there. And again, when you take a log, you want to make sure that the ratio has no dimensions. So both temperatures are to be expressed in Kelvin for that purpose. In the next example, we're going to look at change in the entropy of an ideal gas, where we change both the temperature as well as the pressure. 1 mole of an ideal gas, Cp is 5/2 R, initially at 20 degrees centigrade, and 1 atmosphere pressure is transformed to 50 degrees centigrade and 8 atmospheres pressure, and calculate delta S for this process. So T1 is given, and T2 is given, P1 is given, and P2 is also given. So we are asked to calculate delta S for this transformation. So now immediately recall that delta S needs to be written in terms of both changes in the temperature as well as the pressure. So the relation for that is delta S Cp ln T2 by T1 minus an R ln P2 by P1, where T1 and P1 are the initial temperature and pressure conditions, and T2 and P2 are the final temperature and pressure conditions respectively. Cp is the heat capacity under constant pressure conditions and is the number of moles. R is the ideal gas constant or gas constant. So now substituting the numbers into this in a straightforward manner, and again paying attention to the units under the log terms. So temperature expressed in Kelvin and the pressure expressed in atmospheres. And so the units cancel away, and then you get a pure number for which you can take the log. And so remember, these are natural logs. And so there is R term in the first and also R term in the second. And therefore we have the same units for both terms, and by substituting the numbers in, we get the desired value. And the value turns out to be negative minus 1.836 times 8.314 joules per Kelvin per mole. And so that's your final number that you're going to get. Okay, so now we need to check again and see, does this make sense? So we have started at low temperature 20 degrees and a low pressure at 1 atmosphere. We raise the temperature to 50 degrees. So delta S contribution due to the temperature change will be positive because you're raising the temperature. However, we are raising the pressure also from 1 atmosphere to 8 atmospheres. And therefore, there is also a pressure contribution to the entropy term. But as you increase the pressure, the entropy decreases. So because you have two terms in the opposing directions, so the net will be the difference between the two. And that's exactly what we have calculated here. The difference between two terms, an increase and also a decrease. So depending on whichever is the larger term, that is going to supersede the sign. So in this particular case, the temperature is not changing by many-fold, but whereas the pressure is increasing by 8-fold. So the second term dominates, and therefore we have a value that is negative because the second term has a negative sign in front of it. And that, of course, makes sense because you increase in the pressure, so the entropy needs to decrease. And so despite the increase in the temperature, the increase in the pressure supersedes the change in the entropy from positive to negative. So again, caution here is that we need to make sure the units in the log term need to cancel out. So you can express temperature in Kelvin and pressure in pascals or atmospheres. As long as the units are multiplicative, you're okay. And so be cognizant of that aspect.